our video lecture on orthographic projections. By the end of this lecture, you should be able to state the reasons why orthographic projections are used in engineering drawings, and also make and interpret some isometric drawings. You should be able to explain an orthographic projection, an orthographic drawing or projection, and then also explain the difference between first and third angle projections of orthographic drawings. Okay, so basically, the graphical projections we have, or um, the general graphics we have, can be grouped in the following way. Okay, so there's a general group we have for graphics. Okay, but concerning us, we are going to narrow. We are going to narrow to a smaller number of the details of how drawings are grouped. Okay, so first of all, what if we say an orthographic projection? What is it? Okay, what is it? Or in terms of why we need orthographic projections if there are other kinds of drawings. Now, the first reason is we need to make a drawing that depicts the true size and shape of an entire machine. We need to make a drawing that depicts the true size of an entire machine. Okay. Also, it's very difficult to present a 3D view of an object, okay, on a sheet of paper. All right. Now, for you to see all the details of an object in 3D, you should be able to rotate it, turn it around, and then you have all the details. Okay. By a lot of times, the 3D object we have is actually a 2D representation of the three-dimensional one. So it's on the paper. So you want to look at the object, and you may have to you have no way, because you cannot rotate the object on a sheet of paper. Okay. All right. So the drawings we are going to look at is going to be restricted to all these, to the ones we have in this slide. Okay. So first of all, let's look. We are going to look at two types of projections: pictorial projections and then orthographic projections. Okay. Now, under pictorial, we have isometric, oblique, and perspective drawings. Okay. And under orthographic, we have first and third angle projections. Okay. Now, isometric, which falls under the pictorial drawings. Let's look at some explanation around isometric drawings. Okay. Now, it's a type of drawing that is it's type of a 3D drawing that is set out in angles of 30 degrees. Okay. So you can see here, of both drawings here have edges set out at 30 degrees. Okay. Okay. And then the angle between these lines are 120 degrees. Okay, it's showing here more clearly. Okay, so that's an isometric drawing. Then it is also a form of axonometric drawing. Okay, now when I say axonometric, it means the projections in the line of sight, okay, with which are looking at the object, are all parallel. The projections are parallel. All right. Now, the same scale, since they are axonometric, the same scale that is used for every axis, okay, same scale is used for every axis, okay. And when you do that, your object, your 3D object, is not distorted. It's not distorted. Now, in the natural, when we see objects, they are almost always distorted. Every natural object you see, they are distorted. Okay, some axes of the same object may look smaller or shrink, and then another axis may look bigger or elongated. We'll look at those details later. Okay. Now, also in isometric drawings, measurements can be made to scale along the principal axis. So these are the principal axes, showing with my laser point. Principal axis, principal axis, principal axis. Okay. So these are the principal axes of the isometric drawing. Okay, so let's look at some rules to follow when we are making isometric drawing. All right. Now, horizontal edges, all horizontal edges in isometric drawings, okay, will be drawn at 30 degrees to the horizontal. Okay, will be drawn at 30 degrees to the horizontal. That is why over here a 30-degree set square is being used to draw the horizontal side of this block. Okay, in isometric it will show as inclined, but in reality it's the horizontal side of the block. But if we are drawing in isometric, it will show as inclined at an angle of 30 degrees. So we are using a 30-degree set square. Okay, using a 30-degree set square over here. Sorry, we are using a 30-degree set square. Okay, so another ISO object, another ISO block. We can see the 30 degrees over here. Now this over here, it's this over here is something we call an isometric drawing on an isometric sheet. This is a drawing is made on an isometric sheet. Okay, so when I'm making this drawing, you are making this drawing in the top far right corner. Okay, you do not need a set of drawing instruments. All you need is your straight edge or even your free hand. Okay, you don't need a set square, you do not need your T-square and all that. Okay, no, so 30 degrees for all horizontal edges. Vertical edges are still drawn as vertical lines. Okay, and then parallel edges appear as parallel lines. So this side of the cube, this side of the other side of the cube are still parallel. This side, this line of the block, okay, this line and then this one are still appearing as parallel. And the same goes for all the other drawings, even the one here on the ISO sheet. Okay, the vertical ones still remain vertical. Okay, now we have to mention we have to talk about the concept of an isometric scale. Okay, in other words, when you look at something and when you make an isometric drawing of something, you miss out on the true length of the part. What we have here is a cube, but when you look closely, you see that from this corner of the top to this other corner of the top of the cube to this other corner is not the same as from point A to point B. CD is not the same as point A to point B. Okay, so what is in all these, the part of the cube that is the true length is from point A to point B. That is the true length. But from C to D is not a true length. It's not a true length. Okay. So let's do our math. We have this, we simplify this or spotify the adjacent components of both lines, this one and then this one. Find the adjacent components, and it gives us cos 45 over cos 30. All right, so this gives us a ratio of 0.82, about 0.82. So anytime you have an isometric length, okay, it is equal to 0.82 times the true length. 0.82 times the true length. But most of the drawings will be encountering, for example, when a drawing is given to you to produce the ISO version of it, it's normally the dimensions you'll be giving on such a drawing will be the true length. Okay, we'll see about how this is applied when we start drawing making orthographic drawings. Okay, then we move to the next kind of pictorial drawing. Okay, the first one was ISO. Now we are on oblique. Okay, in oblique, the projection is done in a slanting position. Okay, so one of the edges is made to lie on the horizontal plane. Okay, on one of the edges coincides the horizontal plane, and then the other one is tilted, okay, to an angle of 30, 45, or 60 degrees. Okay, so this one tilted at 30, this one is tilted at 60, and this one tilted at 45. Okay, now oblique projection is a simple type of technical drawing, okay, of graphical projection used for producing two-dimensional images of three-dimensional images. Okay, so there's a three-dimensional image, like I said, you can turn it around, you can look at various parts of this three-dimensional object. Okay, but when it is set on a paper, then it becomes a two-dimensional object. Okay, as long as it's set on the paper, then moving it is restricted. So we have a two-dimensional object. All right, let's look at some advantages of oblique projection. So now the oblique projection represents the exact shape, okay, of an object. Okay, it represents the exact shape of only one face of the object, not the whole object. It represents only one side of the object. Okay, let's look at our oblique drawing again. So this is a cube. Okay, you can see our square here, all right, which is one of the sides of the cube. Okay, but this same square here, all right, tilted at 45, looks like this, all right, which is not a true square. So only one side, this side, only one side, which is only one side, this very side, okay, this side of the square. Okay, now that one is the true shape of one of the sides of the cuboid. So that is what point one is saying, advantage. There's a part of an orthographic drawing, okay, which is the exact shape. All right. Okay. So that is better for elliptical shapes than axiometric projections. So like earlier on, an isometric drawing is an axonometric projection. Okay. Now, when we want to draw a circle, we want to see the full view of the circle, just like we saw in the square, which is at the side of the cube. It's better to draw our circle here. Okay, because when we draw our circle here, it's going to be deformed, become something like an ellipse. Okay, so if we want a true shape, we want to avoid that. We want to have it at the side. We want to have the circle at the side where we have our true face represented, the true shape of the face. Okay, now oblique drawings also lack perspective. Okay, what we call perspective foreshortening. Okay, that's just another way of looking at distortion. All right. Okay, so it lacks perspective, it lacks distortion. Okay, when you compare and you see that lack of distortion makes comparison of different sizes, it makes it difficult. Okay, now it also displays some of the objects three-dimensional appearance. On oblique projection would display some of the objects three-dimensional appearance, which is good because it gives us more information about the objects we are trying to show. Disadvantages: it lacks foreshortening because all realistic objects are foreshortened in one way or the other. That is why when you raise your phone to take a selfie, okay, you notice that depending on where the phone is located, sometimes the selfie might be short or shrink. All right. What you have depends on where you position your phone camera to take your selfie. So in the natural, every picture we take, okay, is distorted to a certain extent, or is foreshortened to a certain extent. All right. Now, another disadvantage is that objects can look distorted if careful choice um, is not made about the position of the projection plane. All right. So that's what I like. What I explained earlier on about the circle and the ellipse on the cube. Okay, the cube in the previous slide. Okay, now we come to perspective projections. So these are the more realistic pictorial view of all of them. These are the more realistic pictorial view. Okay, so when you stand at the one end of a straight road, okay, you see the road vanishing at a point. You see the road vanishing at a point, where we call the vanishing point, okay, or the perspective point. Okay, and then this is imagine yourself standing at one corner of a street and looking at this building. You can see that there seems to be the building, this side of the building seems to be vanishing at this point. Okay, all right. And then we have another instance where you are looking at the building and it seems to be vanishing in three different points. All right. So this is a very, very, very realistic, pictorial drawing. Now, perspective drawings show three-dimensional objects in a single. They also show three-dimensional objects in a single plane as they appear to the eyes. Okay. Up until now, all that we have looked at in isometric drawings, okay, oblique drawings, and then perspective drawings, okay, are all 2D images. Okay, they are 2D impressions of something that is actually 3D. Take note of that. Okay. Now, so now we are looking at multi-view orthographic projections. Multi-view, so many views. Okay, you have so many views depending on what you are interested in, what part of the three-dimensional object we are interested in. We can have as many views about that object as possible. Okay, what are multi-view orthographic projections used for? Okay, so multi-view orthographic projections are used to change physical objects, okay, and three-dimensional ideas into two-dimensional. Okay, so just like we had for the other ones, orthographic projections is just another way, okay, of representing three-dimensional objects in in a two-dimensional way. Okay, now also drawings can effectively, that means the orthographic projections, the multi-view orthographic projections can effectively describe the design and features of an object. Okay, all right, let's look at advantages. We are able to get accurate measurements, okay, in the multi-view orthographic projections, okay, because in this kind of projections there are no distortions. There are no distortions, except in the case where we may be interested in maybe an auxiliary view. Okay, then also all views are on the same scale. We'll see this in the other examples we'll solve on orthographic drawings. Okay, so we are going to try to understand some terminologies associated with orthographic drawings. Okay, now this is a plane. This is a plane where we imagine that our objects are this is an intersection of planes. Okay. Now the 3D drawings you want to make projections of can be placed in any of this quadrants. Okay. But we are interested in the first quadrant, which is over here. First quadrant, which is over here. Okay. And the third quadrant, which is over here. Okay. When you place your object in the first quadrant and you make your orthographic projections, then you are going to have the orthographic projections in first angle projection. But when you have it, when the object is placed here, you're going to have your orthographic projection in third angle. So I'm going to make my drawings in the first quadrant, then I apply these considerations. Now the first one says that the object lies between the observer and the plane of projection. So this is my first quadrant. Okay, that's the vertical plane. And then the horizontal plane. This way. Okay, so I can just write them there. My HP. Okay, and then my vertical plane, my VP. Notes in the first quadrant. Then we see that our object is situated between the observer and the planes. So look at an object, something like an object like this. So the object is small, like a cone. Okay. So our observer is located here, somewhere here. Okay. Now so look at our object in yellow. It fits this description well. It's above the horizontal plane, and then it's in front of the vertical plane. Now 3 says that the front view of the object comes above its top view with respect to the reference line. What is our reference line? This is going to be our reference line going through where the two planes meet. All right. Okay. Now in this description, you see that you'd have to rotate or swivel the horizontal plane for it to be under the vertical plane. So the front view of the object comes above its top view with respect to the reference plane. So if we do that swiveling, we are going to have the top view at the bottom. Oops. You're going to have a top view at the bottom. Okay. We have the reference line. This is our reference line. And our vertical plane. Okay, so you can see that we are going to have our front over here. We're going to have our front over here, and then our plan over here, depending on how you visualize the object, because there can actually be another vertical plane over here. There can be another vertical plane over here. Okay. So if let's relocate the okay. All right, so we are going to have our front something like this. Okay, so we are going to have a front view or something like that. Okay. All right, so I'm going to have a front view that way. We have our reference line as a boundary, and then the plan will also look a similar way, only that it will be located beneath the front view. Okay, let me qualify my planes again. This is our rotated horizontal plane. Okay, and this is our vertical plane. Our vertical plane. All right, so that's for first angle projection. Let's see how it plays out when we get to third angle projection. Let's see how it plays out when we get to third angle projection. Right, now it says the planes of projection lie between the object and the observer. Okay, so let me draw my third quadrant. Okay, so that's the horizontal plane in my third quadrant, and this will be the vertical plane. The vertical plane will be something like this. Okay, all right, and we'll have our reference line. That's it. Okay. This time around, the object is situated above the ground. So let's take it that all this area is the ground. Above the ground, above the ground. Okay. All this space here. Okay, this is your ground. So you can see that there's some space between the ground and the horizontal plane. The object is situated above the ground or below the horizontal plane. Let me get my numbers right again. So this is our horizontal plane and our vertical plane. Vertical plane. Okay. Now object is situated somewhere here. Let's get the object. Okay. So All right, so that's your object. All right, so now we've gone through all this. Now, when you are done, in order to get your projections, you see the top view of the object comes above its front view. Why will it come above its front view? Because in order to put all these on the same plane, in order to put the horizontal plane and the vertical plane on the same flat space, we'll have to rotate the horizontal plane this time around. We have to rotate the horizontal plane. We have to rotate the horizontal plane. Okay, and by doing so, we are going to get this. Okay, then our reference line, and also our vertical plane. And over here, what we have is the rotated horizontal plane. Okay, here we have, again, we are maintaining a vertical plane. This is still our vertical plane. All right, remember, observer is around here. Planes of projection lie between object and observer. Planes of projection, vertical plane, horizontal plane, they lie between object and observer. So observer is actually observing from somewhere. So this is the eye of the observer, and you have to see through the plane before he sees the object. So we are going to have our front elevation over here. That way. And then our front elevation and our top view. So front view, and then we are going to have our top view. It's going to be a similar thing because it's a cone. The object is a cone. Okay. So now we go to the next. Okay. Now almost the same thing happens for the envelope we picked from the third quadrant. The envelope we picked from the third quadrant. Almost the same thing happens. Okay. But you see that the top envelope, okay, is what you have in the green. All right. Now, if the observer is interested in looking at the front view, you have to look through another envelope to see the object. So observer is here, there is something between him and then the object. Okay, so you have to look through another envelope, which originally is not here. Okay. Now, when he observes from here, from above, to have the top view, okay, this is what you see drawn on the envelope. Okay, so now we are rotating the horizontal plane. Here in the first angle, we rotated the horizontal plane. Okay, so again, we are rotating our horizontal plane. So we are going to have our rotated horizontal plane over here. So the rotated horizontal plane. Okay. Okay. And the part here in blue is this envelope over here. Okay, the part of the rule in blue is what we have over here, which is actually part of the horizontal plane. All right, so the view, if you are looking towards the side, it will get, so observer will be here, observer is over here, and then there is something like a screen before he sees the object. Okay, so again, the plane will have to be rotated in order to flatten it, rotated in order to flatten it. Okay, so those are the explanation of why we have orthographic projections, either in first angle projection or in third angle projection. All right, so here are the differences. Here are the difference clearly. In first angle projection, when you have the front view, the top view is beneath it. All right, you have the front view, the top view is beneath it. Okay, take very good note of this. You have the front view, and your top view is beneath it, and then the front view will have its right view located on the left of the drawing. Okay, and then its left view, when you're looking at the object from the left, is actually located on the right hand side of the drawing. Okay, you can look, when you look at the previous slide again, you can see that, you can make that out. Then when you come here to, in third angle projection, whatever is the left view is located on the left view. All right, whatever is being called the right view is truly located on the right hand side of the front view. Okay, and then the top view is now at the top of the front view. So take very good note of that relation in both cases. Okay, very, very, very important. Okay, and then again, we look at their symbols too. Look at their symbols. Now, in first angle projection, what you see, if you see from the left, you're looking at the object from the left, you have to locate it, what you see on the right hand side of the object. And then the reverse is true for third angle projections. Okay. We just apply the same thing: top view, right end view, left end view, and then bottom view, okay, to a car. All right, so that you look closely at it and you see the differences. All right, so the differences between first and third angle are stated out clearly here again. You can look at it in summary of this video lecture. So what have we done today? We have looked at so in summary, we've stated the reasons why orthographic projections are necessary. Okay, apart from all the other pictorial drawings we have, isometric and orthographic. Okay, and we also took our time to get the explanation for the difference between first and third angle projections. Thank you very much. Like my videos. See you in the next tutorial.